Hello guys, this is the EdExcel AS level further maths paper 1, which covers the core pure maths section, and this is from the sample papers. So let's get straight into it. Question 1. F of z is equal to z cubed plus pz squared plus qz minus 15, and p and q are real constants. Given that the equation f of z equals 0 has roots alpha, 5 over alpha, and alpha plus 5 over alpha minus 1, for part A, we have to solve completely the equation f of z equals 0. Now, I will begin by first of all labelling the coefficients of this cubic equation a, b, c, and d. We notice over here a is equal to 1, b is equal to p, c is equal to q, d is equal to minus 15. And just for clarity, because we have 3 different roots over here, I will label these roots alpha, beta, and gamma. So beta over here is 5 over alpha, and gamma is alpha plus 5 over alpha minus 1. So with that being said, we can use the product of alpha, beta, and gamma equaling minus d over a. So with that being said, for part A, using alpha, beta, gamma equals minus d over a, we have alpha multiplied by beta, which we said was 5 over alpha, multiplied by gamma, which we said was alpha plus 5 over alpha minus 1. And this is equal to minus d over a, so we have minus 15 over 1. So we have minus 15 over 1. And now, simplifying all this, you will first of all notice the alphas over here cancel, and the minus and a minus give a plus. So we have 5 lots of alpha plus 5 over alpha minus 1 equals, here we have 15. And if I divide through by 5, we see that alpha plus 5 over alpha minus 1 equals 3. And we can solve this equation. First of all, multiplying through by alpha. Alpha times by alpha is alpha squared. Then we have 5. And then minus 1 times by alpha, that's minus alpha. And this is equal to 3 times by alpha, which is 3 alpha. And if we simplify this, we have alpha squared minus 4 alpha plus 5 equals 0. Now we can solve this equation. So, alpha is equal to minus 4 plus minus 4 squared minus 4 lots of 1 lots of 5, and then this is square rooted, and then we divide by 2a, so we divide by 2 lots of 1. And if we work this out, let's just grab our calculator. So press menu and then go to the equation section. We have a polynomial of degree 2 with coefficients 1, minus 4, and 5. We end up with alpha equaling 2 plus I and 2 minus I. So we have 2 plus minus I. Now, we have two roots over here. We can find our third root by substituting into this alpha plus 5 over alpha minus 1. So with that being said, the other root will be alpha plus 5 over alpha minus 1. So we have 2 plus I plus 5 over 2 plus I minus 1. Of course, this is the same as 2 minus I plus 5 over 2 minus I minus 1. So if we go to our calculator, let's turn the mode into complex mode. And if we enter that in, we have 2 minus I. So we have 2 minus I plus 5 over 2 minus I minus 1. We end up with a value of 3. So with that being said, we can therefore conclude over here that the roots of f of z equals 0 are z equals 2 plus minus I and also 3. Okay, and now for part B, hence find the value of p. Well, we can use the sum of the roots alpha plus beta plus gamma equals minus b over a. So let's just write that down. Using alpha plus beta plus gamma equals minus b over a, we have alpha, which is 2 plus I, plus beta, which is 2 minus I, plus gamma, which is 3. And this is equal to minus p over 1. And over here, you will notice we have 2 plus 2, which is 4, plus another 3, that's 7. So we see that 7 is equal to minus p is equal to minus 1. And with that being said, we can therefore conclude over here that f of z is equal to z cubed minus 7z squared plus qz minus 15. Okay? Question 2. The plane pi passes through the point A and is perpendicular to the vector n. Given that OA is equal to 5 minus 3 minus 4 and n is equal to 3 minus 1, 2, where O is the origin, we have to find a Cartesian equation of pi. Now, if you go to your formula book, you will notice in the vectors section over here, if we have a plane through A with normal vector n with components I, j and k, and the coefficients of I, j and k are n1, n2 and n3, then this would have Cartesian equation n1x plus n2y plus n3z plus d equals 0, where d is equal to minus a dot n. So if we take this d over to the other side, we would have minus d, and therefore minus d will equal a dot n. So the minus essentially goes to the other side. Now, if we find out this value of d, we know the coefficients of n. From that, we can determine the Cartesian equation of pi. So over here, I will highlight this. We will be using this in the formula book. So with that being said, the first thing we can do is we can dot product OA with n to determine the value of D. So with that being said, for part A, we have n dot product with OA. So we have the vector n, 3 minus 1, 2, dot product with the vector OA, which is 5 minus 3 minus 4. So 3 times by 5 plus minus 1 times by minus 3 plus 2 times by minus 4. We have 15 plus 3 minus 8, which is 10. And therefore we can conclude our Cartesian equation of pi. The Cartesian equation of pi would be 3x minus y plus 2z equals 10. For part B, we have the line L over here with respect to a fixed origin O is given by the equation R equals 7, 3 minus 2 plus lambda lots of minus 1 minus 5, 3. And this line L intersects the plane pi at the point x. We have to show that the acute angle between the plane pi and the line L is 21.2 degrees, correct to 1 decimal place. Now, to do this question, we would first of all have to recognize that the acute angle is given by sine of theta equals the absolute value of B dot product with n over the absolute value of B multiplied by the absolute value of n. So with that being said, all we have to do over here, if we consider this minus 1, minus 5, 3, essentially this bit over here is our B, and we know what n is. That was 3 minus 1, 2. So with that being said, first of all, working out the dot product between the 3, the minus 1, 2, and the minus 1, minus 5, and the 3. We have over here 3 times by minus 1 plus minus 1 times by minus 5 plus 2 times by 3. So we have minus 3 plus 5 plus 6. The value of this is 8. Now we can find out the magnitude of B and the magnitude of n. So first of all, if we consider this vector over here, we have 3 squared plus minus 1 squared plus 2 squared square rooted 9 plus 1 plus 4, which is 14. So we have the square root of 14. And then, if we consider this vector over here, we have minus 1 squared plus minus 5 squared plus 3 squared square rooted 1 plus 25 plus 9, that's 35. So we have the square root of 35. And now if we substitute our values into this equation, we can therefore say that sine theta is equal to 8 over the square root of 14 times by the square root of 35. So if we work this out with our calculator, first of all, make sure our calculator is in degrees. 8 over root 14 lots of root 35. That would equal 4 root 10 over 35. So we have 4 root 10 over 35. And therefore, theta, if we work this out, the inverse sine of this would be 21.186, etc. So we have 21.186, etc. degrees. Theta, therefore, is equal to 21.2 degrees to 1 decimal place. And now, for part C, we have to find the coordinates of this point x. Well, to do this question, I will rewrite the equation R as 7 minus lambda, 3 minus 5 lambda, minus 2 plus 3 lambda. Okay? What we have over here then is our equation for R. We have n, and if we dot product these two together, this will equal this 10 over here, and you may know that from your notes. So with that being said, the line meets the plane when we have 7 minus lambda, 3 minus 5 lambda, and minus 2 plus 3 lambda, dot product with 3 minus 1, 2, equals 10. So if we work this out, we have 3 lots of 7 minus lambda plus minus 1 lots of 3 minus 5 lambda, and then we have 2 lots of minus 2 plus 3 lambda, and all this is equal to 10. So 3 times by 7, that's 21. 3 times by minus lambda, that's minus 3 lambda. And then here we have minus 1 times by 3, which is minus 3. Minus 1 times by 5 lambda, which is 5 lambda. 2 times by minus 2, that's minus 4. 2 times by 3 lambda, that's 6 lambda. And this is equal to 10. So with that being said, collecting like terms, we have 8 lambda plus 14 equals 10. 8 lambda is equal to minus 4. And therefore we can see over here, lambda is equal to minus 0.5. And with that being said, we can now find OX by substituting back into over here. We can therefore conclude that OX will equal 7 minus 0.5, 3 minus 5 times by minus 0.5, and minus 2 plus 3 times by minus 0.5. The result of this, we have 7.5, 5.5, and minus 3.5. Of course, the coordinates of x would be 7.5, 5.5, and minus 3.5. Question 3. Tyler invested a total of £5,000 across 3 different accounts: a savings account, a property bond account, and a share dealing account. Tyler invested £400 more in the property bond account than in the savings account. After 1 year, the savings account had increased in value by 1.5%. The property bond account had increased in value by 3.5%. The share dealing account had decreased in value by 2.5%. The total value across Tyler's 3 accounts had increased by £79. We have to form and solve a matrix equation to find out how much money was invested by Tyler in each account. Well, if we call the savings account X, if we call the property bond account Y, and the share dealings account Z, so let's just highlight these pieces of information. We have the savings account, which we'll denote as X, the property bond account, which we'll denote as Y, and the share dealings account, which we'll denote by Z. With that being said, we first of all know that he invested a total of £5,000 across these different accounts. So we have X plus Y plus Z equals 5,000. We also know that Tyler invested £400 more in the property bond account, which is Y, than in the savings account, which is X. So we can say over here then that X plus 400 equals Y. And if I rewrite this, we can rewrite this as X minus Y plus 0Z equals minus 400. And the reason I'm doing that will become clear later on in this question. And now using what we know after 1 year, if we consider all these percentages as multipliers, the total value across Tyler's 3 accounts had increased by £79. So therefore, if we include all these multipliers, we have a total of 5079. What we mean by that, we have 1.015x plus 1.035y plus 0.975, and the reason it's 0.975 is because we're decreasing by 2.5%. We end up with a total of 5097. So we have 3 equations over here. We have this equation, the second equation, the third equation here. We have 3 unknowns, x, y, and z, and therefore we can solve these equations simultaneously in matrix form. So in matrix form, we can therefore say that we have our first equation 1x plus 1y plus 1z. In matrix form that would be 1, 1, 1. For the second equation we have x minus y plus 0, so we have 1x minus 1y plus 0z. And for our final equation we have 1.015x, 1.035y, 0.975z. Obviously we have x, y and z as our vector which we're solving. And this would be equal to 500, so that's for the first equation. Sorry, 5,000 rather. Our second equation, we see we have minus 400. Our third equation, we have 5097. We can quite easily solve for x, y and z. To do so, we would have to find the inverse matrix of this 1, 1, 1, 1, minus 1, 0, 1.015, 1.035, 0.975, 0.75. Remember, we raise this to the power of -1 because we're finding the inverse of this. And then we multiply this by 5,000 minus 400, 5097. So if we work this out, we can do so with our calculator. So if we grab our calculator, and if we go to the matrix mode, we will define matrix A. Matrix A has 3 rows, 3 columns, and it has components. If we write these down, we have 1, 1, 1, 1, minus 1, 0, 1.015, 1.035, 0.975. So that's our matrix A. We press AC to eliminate that. We will now define matrix B. So press options number 1. We will define matrix B. This has 3 rows, 1 column, with components 5,000 minus 400 and 5097. So 5079. That's our matrix B defined. So what we want to do is find the inverse of matrix A and multiply this by matrix B. We get 1800, 2200 and 1000. And with that being said, we can therefore conclude the following. We can therefore conclude that Tyler invested £1,800 in X, £2,200 in Y, and £1,000 in Z. Question number 4. We have a cubic equation x cubed plus 3x squared minus 8x plus 6 equals 0, and this has roots alpha, beta, and gamma. Without solving the equation, we have to find the cubic equation whose roots are alpha minus 1, beta minus 1, and gamma minus 1, giving your answer in the form w cubed plus pw squared plus qw plus r equals 0, where p, q, and r are integers to be found. Well, as with any cubic, let's define A, B, C, and D. For the cubic involving x's, A is equal to 1, B is equal to 3, D is equal to minus 8, C is equal to minus 8, D is equal to 6, and considering our cubic in W, A is equal to 1, B is equal to P, C is equal to Q, D is equal to R. Knowing that, if we consider our cubic in X, let's use the sum roots. So using the sum roots, which is obviously alpha plus beta plus gamma equals minus b over a. We have over here alpha plus beta plus gamma equals minus b, so we have minus 3 over a, which is 1, so we have minus 3. And now if we use the pair sum, so using the pair sum, we have alpha beta plus beta gamma plus alpha gamma equals c over a. C is equal to minus a is equal to 1. So we have alpha beta plus beta gamma plus alpha gamma equals minus 8 over 1, which is minus 8. And if we use the product, so using product, that is alpha, beta, gamma equals minus d over a. We know d is equal to 6, a is equal to 1. So alpha, beta, gamma is equal to minus 6 over 1, which is minus 6. So all this over here is for our cubic involving an x. And we know already, if we consider our cubic involving a w, that has roots alpha minus 1, beta minus 1, and gamma minus 1. So we can do the exact same thing as we did over here, but this time, instead of using alpha, beta, and gamma, we will be using alpha minus 1, beta minus 1, and gamma minus 1. I'll do this in a different colour for clarity. If we consider the sum roots, the sum roots will be alpha minus 1 plus beta minus 1 plus gamma minus 1, and this will equal minus p over 1. And the reason it's equal to minus p over 1, same thing as before, we have minus b over 1, so we have minus p over 1. And if we simplify all this, we have alpha plus beta plus gamma, and then minus 1, minus 1, minus 1, that's minus 3. And then we have that equaling minus p. Alpha plus beta plus gamma, we just found that to be minus 3. So we have minus 3 minus another 3 equals minus p. P is equal to 6. So just for clarity, this minus 3 came from here, which is alpha plus beta plus gamma. And similarly, if we use the pair sum, so using the pair sum, we have alpha minus 1 lots of beta minus 1 plus alpha minus 1 lots of gamma minus 1 plus beta minus 1 lots of gamma minus 1. And this is equal to, if we use what we had over here, c over a, that will equal q over 1. Okay? So, if we expand all this out and simplify, alpha times by beta, we have alpha beta. Alpha times by minus 1, that's minus alpha. Minus 1 times by beta, that's minus beta. Minus 1 times by 1, that's 1. Alpha times by gamma, that's alpha gamma. Alpha times by minus 1, that's minus alpha. Minus 1 times by gamma, that's minus gamma. Minus 1 times by minus 1, that's 1. Beta times by gamma, that's beta gamma. Beta times by minus 1, that's minus beta. Minus 1 times by gamma, that's minus gamma. Minus 1 times by 1, that's plus 1. And this is equal to q. So we have alpha beta, alpha gamma, and beta gamma. Let's just write that down. We have alpha beta, alpha gamma, and beta gamma. And then we have minus alpha minus beta, minus alpha minus gamma, minus beta minus alpha. So we have minus 2 lots of alpha plus beta plus gamma. And then we have 1 plus 1 plus 1, which is 3. And all this is equal to q. Now, alpha beta, alpha gamma, and beta gamma, that was minus 8. So this minus 8 comes from over here. So let's just highlight that. for clarity. And then we have minus 2 lots of alpha plus beta plus gamma, which we found to be minus 3. So we highlight that in yellow. And then we still have this plus 3. And this is equal to Q. Q, if we simplify all this, we see over here that Q is equal to minus 1. And now, if we consider the product, we have alpha minus 1, beta minus 1, gamma minus 1. And this is equal to, if we go back and use what we had over here, that's minus d over a, which is minus r over 1. So we have minus r over 1. So we have alpha minus 1, and if we expand beta minus 1 lots of gamma minus 1, we have beta gamma minus beta minus alpha plus 1. And this is equal to minus r. So with that being said, let's now expand alpha times by beta gamma, that's alpha beta gamma. Okay. Alpha times by minus beta, that's minus alpha beta. Alpha times by minus gamma, that's minus alpha gamma. And alpha times by 1, that's alpha. Then minus 1 times by beta gamma, that's minus beta gamma. Then minus 1 times by minus beta, that's plus beta. Then minus 1 times by gamma, that's plus gamma. And finally, minus 1 times by 1, that's minus 1. And all this is equal to minus r. So we have alpha beta gamma, and then we subtract off alpha beta plus alpha gamma plus beta gamma, and then we add on alpha plus beta plus gamma, then we subtract 1. All this is equal to minus r. Now alpha beta gamma, we found that to be minus 6, so let's just highlight this. So we have minus 6 minus, now we found alpha beta plus alpha gamma plus beta gamma to be minus 8, and alpha plus beta plus gamma, we found that to be minus 3. So let's just color code all this as necessary. And then we still have this extra minus 1, and this is equal to minus r. R is equal to 2. So with that being said, we can therefore conclude, knowing the values of p, q and r, we have w cubed plus 6w squared plus w plus 2 as our cubic equation. Okay, so don't forget we have an equals 0. Question 5. We have a matrix M which is given by 1 minus root 3, 1. And for part A, we have to show that M is non-singular. To do this question, we would first of all have to find the determinant of M, and if that doesn't equal 0, we can conclude that M is non-singular. So to find the determinant, we have 1 times by 1 minus root 3 times by root 3. So for part A, the determinant of M is equal to 1 times by 1 minus root 3 times by root 3. So we have 1 plus 3, which is 4. And because this doesn't equal 0, we can therefore conclude that the matrix M is non-zero. singular. Now for part B, the hexagon R is transformed to the hexagon S by the transformation represented by the matrix M. Given that the area of hexagon R is 5 square units, we have to find the area of hexagon S. Well, this 4 over here corresponds to an area scale factor. Okay? And therefore, the area of S will equal 4, which is our area scale factor, multiplied by 5, which is the area of the hexagon. We end up with 20 units squared. Now for part C, the matrix M represents an enlargement with center 0, 0 and scale factor k, where k is greater than 0, followed by a rotation anti-clockwise through an angle of theta about the origin. We have to find the value of k. Well, k over here is a scale factor, so therefore we have our area scale factor and therefore our linear scale factor. And the reason I say linear scale factor, if we go back to the question, we were told we have an enlargement, hence we have a linear scale factor. The linear scale factor k is equal to the square root of the digit of m. So we have the square root of the 4, which is 2. And now for part D, we have to find the value of theta. Now, when we have a combination of transformations, we would have to work backwards. So let's just write this down. We would have to work backwards. In other words, in the question we were told we have an enlargement followed by a rotation. So when we work backwards, we do the rotation first, followed by the stretch or the enlargement. So with that being said, if we have a look at the rotation, going back to our formula book, an anti-clockwise rotation through theta about the origin is given by this formula over here. So with that being said, this is our rotation matrix. So we have cos theta minus sine theta, cos theta. So this was our rotation. Maybe if we highlight this, so the rotation is this matrix over here. And then we have our enlargement. Now, because we have that matrix would be 2, 0, 0, 2. So this represents the enlargement. Okay? And if we multiply these matrices together, we end up with the matrix M. So these two multiplied together gives our matrix M 1 minus root 3, and 1. So with that being said, let's now find the result of multiplying this rotation matrix with the enlargement matrix. We have let's just be clear about this. For our first element, cos theta times by 2. So we have 2 times by cos theta, and then we have minus sine theta times by minus sine theta times by this 0 over here. So we have minus sine theta times by 0. That's our first element. For our next element, we have cos theta times by 0. So we have cos theta times by 0 plus minus sine theta times by 2. So we have 2 times by minus sine theta. Then we have sine theta times by 2. So we have 2 times by sine theta. And then we add on cos theta times by 0. And finally, we have sine theta times by 0. And then we have cos theta times by 2. So we have 2 times by cos theta. And if we simplify all this, we end up with 1 minus root 3, and 1. So we have 2 cos theta minus 2 sine theta, 2 sine theta, 2 cos theta equals 1 minus root 3, 1. And if we compare, so for example, if we take a look at the 2 cos theta and compare that with the 1, we have 2 cos theta equals 1. And if we compare the minus 2 sine theta with the minus root 3, we have minus 2 sine theta equals minus root 3. So here we can see that cos theta equals 1/2, and here we can see that sine theta is equal to root 3 over 2. So with that being said, if we divide the equations by each other, we can see over here then that sine theta over cos theta equals root 3 over 2 over 1/2. And with that being said, sine theta over cos theta, that's tan theta. And tan theta, therefore, is equal to root 3. From which we can see theta is equal to 60 degrees in radians. That's pi over 3. Question number 6. We have to prove by induction that for all positive integers n, the sum from r equals 1 to n of r squared equals 1/6 lots of n plus 1 lots of 2n plus 1. Well, our first step in a proof by induction question is our basis step. And what we mean by this is that we consider what happens when n equals 1. And when n equals 1, our left hand side, we have the sum from r equals 1 to 1 of r squared. That would simply be 1 squared, which is 1. And our right hand side, if we substitute in 1 into this right hand side, we have 1/6 lots of 1, lots of 1 plus 1, lots of 2 times by 1 plus 1. So we have 6 over 6, which is 1. And what we see over here is that since the left hand side is equal to the right hand side, the summation formula is true for n equals 1. So let's just write that down. Now, with that being said, our second step would be our inductive step. And what do we mean by this? Well, over here, essentially, we can rewrite the sum from r equals 1 to r equals k plus 1 of r squared. We can rewrite that as the sum from r equals 1 to r equals k of r squared. So we simply add up the terms up to k, and then we add on the k plus 1th term. So if we substitute in k plus 1 for r, we have k plus 1 squared. Now, the sum from r equals 1 to k of r squared, we know that the sum from r equals 1 to n of r squared is this thing over here, so we simply replace n with k. So we have 1/6 lots of k, lots of k plus 1, lots of 2k plus 1, and then we add on this extra k plus 1 all squared. So with that being said, our next couple of steps is simply a bit of algebra. And what we want to end up with is essentially, instead of us having an n, our end goal is to end up, let's just write this down, we want to end up with, instead of having an n, we want to end up with a k plus 1 instead of an n. So we have a 6 lots of k plus 1, lots of k plus 1 plus 1, lots of 2 lots of k plus 1 plus 1. This is our end goal. So we need to somehow show that this thing over here is the same as this bit in green, which I've just written down. So with that being said, we see over here, we can factorize out a 6 lots of k plus 1. And inside the big bracket, we have 2k plus 1. And then we add on 6 lots of k plus 1. And don't forget, we still have this extra k over here. And the reason we have 6 over here is because 1/6 multiplied by 6 gives the 1. And if we expand and simplify, we have a 6 lots of k plus 1, lots of 2k squared plus k plus 6k plus 6. Okay, and if we simplify this a bit more, we have 1/6 lots of k plus 1, lots of 2k squared plus 7k plus 6. And we can factorize this bit. If we grab our calculator, we'll do this in a different colour actually. Essentially, we require two numbers which multiply to give 2 times by 6, which is 12, which add to give 7. You'd find these two numbers to be 3 and 4, so we can rewrite the 7k in terms of what we've just found. So we have 2k squared plus 4k plus 3k plus 6. So we have 2k lots of k plus 2 plus 3 lots of k plus 2, which if we group the terms together, we have 2k plus 3 lots of k plus 2. So with that being said, we have 1/6 lots of k plus 1, and here we can rewrite this as k plus 2 lots of 2k plus 3. Now, we can rewrite all of this as 1/6 lots of k plus 1. And the k plus 2, we can rewrite that as k plus 1 plus 1. So instead, I'm going to write this in a big bracket. So we have k plus 1 plus 1, which is the same as k plus 2. And then we have over here 2 lots of k plus 1 plus 1, which if I simplify all this, that's 2k plus 3. Okay, and therefore we can conclude that the summation formula is true when n equals k plus 1. So let's just write that down. We see over here then that the summation formula is true when n equals k plus 1. Our next step, and our final step as well, is our conclusion step. That is to say, because over here it's true for n equals 1, we can say that the summation formula is true for n equals k, and because of that, it's true for n equals k plus 1, we saw that, and because the result is true for n equals 1, it's therefore true for n equals any positive integer by induction. So what we mean by this, we saw that the result was true for n equals 1, and if we increase n by an increment of 1, it's true for n equals 2, and then using this, n equals 3, n equals 4, etc. So therefore, this statement, this original statement, is true. Now, for part B of the question, we have to use the standard results for the sum of r equals 1 to r equals n of r cubed and r equals 1 to r equals n of r to show that for all positive integers n, the sum from r equals 1 to n of r lots of r plus 6 lots of r minus 6 equals a quarter lots of n plus 1 lots of n minus 8 lots of n plus 9. Well, to do this question, this thing on the left hand side is equal to the sum from r equals 1 to r equals n of r lots of r squared minus 36. So we have the sum from r equals 1 to r equals n of r cubed minus 36r, which is the same as the sum from r equals 1 to r equals n of r cubed minus 36 lots of r from r equals 1 to r equals n. Okay? And knowing that piece of information, we can therefore say we already know what the result is from r equals 1 to r equals n of r cubed. If we go to the formula book, you'd find that result over here. And the sum from, if I write this down over here, the sum from r equals 1 to n of r, that's equal to 1/2 n lots of n plus 1. That's a standard result, which you should know. So we will also be using this over here. So with that being said, we can rewrite this entire thing then for part B. We have over here the sum from r equals 1 to r equals n of r cubed minus 36 lots of the sum from r equals 1 to r equals n of r. From r equals 1 to r equals n of r cubed. That would be 1/4 lots of n squared lots of n plus 1 squared. Then we subtract off 36 lots of 1/2 lots of n plus 1. So we have 1/4 n squared lots of n plus 1 squared minus 18 n lots of n plus 1. We can take out 1/4 n lots of n plus 1 as a common factor, and then inside the bracket we have n lots of n plus 1 minus 72, because 1/4 times by 72 gives the 18. With that being said, we have 1/4 n lots of n plus 1, and here we have n squared plus n minus 72. We can factorize that. N squared plus n minus 72 we can factorize as n minus 8 lots of n plus 9. Okay, and that's what we wanted to show. For part C, hence find the value of n that satisfies the sum from r equals 1 to n of r lots of r plus 6 lots of r minus 6 equals 17 lots of r equals 1 to r equals n of r squared. Well, to do this, we already know, if we go back over here, that this left hand side over here is the same as this bit over here, and this bit over here, that is the same as this bit over here. So with that being said, using all that information, we can therefore say that we have 1/4 lots of n plus 1 lots of n minus 8 lots of n plus 9. Okay, so that was the bit that we highlighted in the blue. So let's just highlight that again. This is equal to 17 lots of 1/6 lots of n plus 1 lots of 2n plus 1. That's the bit in green. And the rest of this is just algebra. So, first of all, you'll notice that the n here and here cancels, and the n plus 1 here and here cancels. And then we have 17 over 6 on the right hand side, and on the left hand side we have 1/4. So we have 1/4 lots of n minus 8 lots of n plus 9 on the left hand side, and on the right hand side we have 17 over 6 lots of 2n plus 1. And if we simplify all this, if I multiply by 6 and then divide by 17, we have 3 over 34 lots of n minus 8, let's write this neatly, lots of n plus 9, and this is equal to 2n plus 1. Multiplying through by 34 and then on the left hand side expanding the 3, we already know rather that if we simplify this a bit more, n minus 8 lots of n plus 9, that's n squared plus n minus 72. So we have 3 lots of n squared plus n minus 72 equals 34 lots of 2n plus 1. So we have 3n squared plus 3n minus 216 on the left hand side, and on the right hand side we have 68n plus 34. And if we simplify this quadratic, we have 3n squared minus 65n minus 250 equals 0. And now we can use the quadratic formula to solve for n. N is equal to minus 65 plus minus 65 squared minus 4 lots of 3 lots of minus 250, and this bit is square rooted, and then we divide by 2 lots of 3. So with that being said, if we grab our calculator and then go into the equation section, we have a polynomial of degree 2 with coefficients 3, minus 65 and minus 250. We end up with 25 and minus 10 over 3. So we see that n is equal to minus 10 over 3 and 25. And since over here n must be greater than 0, we can therefore conclude n is equal to 25. Okay? Question number 7. We have figure 1 over here, which shows the central cross-section AOBCD of a circular bird bath, which is made of concrete. Measurements of the height and diameter of the bird bath and the depth of the bowl of the bird bath have been taken in order to estimate the amount of concrete that was required to make this bird bath. Okay? And we have, using these measurements, the cross-sectional curve CD, shown here, shown in figure 2, which is modelled as a curve with equation y equals 1 plus kx squared, where x is in between minus 0.2 and 0.2, and k here is a constant, and O is the fixed origin. The height of the bird bath measured 1.16 meters, and the diameter AB of the base of the bird bath measured 0.40 meters, as shown in figure 1. We have to suggest the maximum depth of the bird bath. Okay. So to do this question, first of all, we've got this equation over here, y equals 1 plus kx squared, that was given here. And essentially we've got this curve of the quadratic bit. And when x is equal to 0, y is equal to 1. So what this means is, this point over here is 1. And we've got this total height, which is 1.16 meters, and therefore the depth of the bowl, which is this remaining bit, which I will show in green, that will equal 1.16 minus the 1, which is 0.16. For part A, we have the depth of the bowl, which is 0.16 meters. For part B, we have to find the value of k. Well, when x is equal to 0.2, y is equal to 1.16. So with that being said, let's write down those conditions. X equals 0.2, y equals 1.16. Using these conditions, we have 1.16 equals 1 plus k lots of 0.2 squared. We can find the value of k. That would be 1.16 minus 1 divided by 0.2 squared, the result of which is 4. And therefore we can conclude over here y is equal to 1 plus 4x squared. Okay? So let's just write that down. We have y equals 1 plus 4x squared. Now, for part C, we have to find the volume of concrete that was required to make the bird bath according to this model. Give your answer in meters cubed, correct to 3 significant figures. Well, essentially, we want to find out this area over here, we want to find the area of A, O, B, C, D. Now, the way to think about this, we can work out the volume of the cylinder. And the reason I say cylinder is because essentially this shape is a cross-section and it's rotated 360 degrees. So in this question, we're actually assessing the volume of revolution. Okay? So the way to think about this is what essentially we need to do is, first of all, find the volume of the following region. So in this question, essentially, we want the bit in red. We can find out the volume of the blue bit using volumes of revolution, and then the outline bit, that's supposed to represent the cylinder. So if we subtract the volume of essentially this ball bit from the volume of the cylinder, we can then find the red bit. Now, if we use volume of revolution, that's the blue bit over here. I'll write this down in black. With volume of revolution, we have the following formula. So for part C, we have over here the volume of the ball that will equal pi lots of the integral from A to B of x squared dy. So this is volume of a revolution. We're essentially rotating something 360 degrees about the y-axis. And we can find out what x squared is from here. So x squared over here will equal 1/4 lots of y minus 1. And with that, we can find our limits. We are going from, if we go back over here, from y equals 1 to y equals 1.16. So those are our limits. And therefore what we have over here then, the volume of the ball will equal pi lots of the integral from 1 to 1.16 of 1/4 lots of y minus 1 dy. And if I factorize out the quarter, we have pi over 4 lots of the integral from 1 to 1.16 of y minus 1 dy. So, if we add 1 to the power and divide by the new power, we have a half y squared. Integrating minus 1, we end up with minus y. And then we therefore have a 1/4 pi lots of, we're evaluating a 1/4 pi lots of a half y squared minus y in between the limits 1 and 1.16. So with that being said, what this is equal to then, we have pi over 4, and then for our upper limit, we have 1.16 squared over 2 minus 1.16. For our lower limit, we have 1 squared over 2 minus 1. Work this out. So we have this is open up our brackets, we have 1.16 squared over 2 minus 1.16 minus a half minus 1 So we end up with pi over 4 lots of this. So if I divide this by 4, we end up with 2 pi over 625 meters cubed. Okay. And the volume of the cylinder we can work out. We know that the diameter of the cylinder is 0.4 meters and therefore the radius is 0.2 meters. So the volume of the cylinder that will equal pi r squared lots of h. So we have pi lots of 0.2 squared lots of 1.16. So times by 1.16, which is 29 over 625 pi. Okay. And therefore, the required volume of concrete, which is the bit shown in red, the volume of the concrete will equal this bit, the 29 pi over 625, minus the bit in blue, which is 2 pi over 625. I'm working this out. So if I subtract 2 over 625, we end up with 27 pi over 625. So let's just multiply this by pi. Therefore, we end up with, as a decimal, 0.136 meters cubed. Okay? And this is to 3 significant figures. For part D, we have to state a limitation of the model. We have the following reason. The measurements obviously may not be accurate. And finally, for part E, it was later discovered that the volume of concrete used to make the bird bath was 0.127 meters cubed, correct to 3 significant figures. And using this information and the answer to part C, we have to evaluate the model explaining your reasoning. We have the following reason. So we might not expect the actual amount of concrete to exceed that which the model predicts due to wastage, and therefore the model does not look suitable since it predicts more concrete than was used. So there might be some waste concrete essentially. So essentially the model has more concrete than we actually use because of that waste, which is produced as a result of building this bird bath. So hopefully that question makes sense. Question number 8. For part A, we have to shade on an Argand diagram the set of points where, for a set of complex numbers, the mod of z minus 4i is less than or equal to 3, and for a set of complex numbers, the argument of z plus 3 minus 4i is greater than minus pi over 2, but less than or equal to pi over 4. Now, before we do this question, it would help if we rewrite this first bit in the form z minus z1 modded being less than or equal to 3. And for this other bit, it would help if we rewrite this in the form of the argument of z minus z2 being greater than minus pi over 2, but less than or equal to pi over 4. So, essentially, if we do the first bit in blue, for part A, for a set of numbers, we have z minus, and then in brackets I will put 0, plus 4i. Okay, this is less than or equal to 3. And we have, for a set of complex numbers, we have the argument of z minus 3 plus 4i being greater than minus pi over 2, but less than or equal to pi over 4. And with this from here, we can see that we have a circle with center 0, 4 and radius 3. Okay, and here we see that we have a half line from the point minus 3, 4. Okay, sorry, this should be a minus over here, because minus minus 3 gives 3. So therefore we have a half-life from minus 3, 4. Now, if we actually draw this first bit and this second bit separately, we'll then combine the results. Okay, so let's just draw on ourselves a quick set of axes. So let's just draw on a quick circle with radius. Okay, we have something which looks like that, approximately. Okay, so what we have over here then, if I draw this more neatly, so having drawn the circle, we want where this circle is less than or equal to 3. Remember, it has a radius of 3, and where it's less than or equal to 3 would essentially, if I shade that here, that would be this particular region over here. Okay, so let's just shade this in. That satisfies this bit over here. And for the next bit, where we have a half line from minus 3, 4, minus 3, 4 is over here, and this must be greater than minus pi over 2. Minus pi over 2 starts here, and because it's a strong inequality, we showed that with dotted lines. So if you imagine a sort of a line over here, from this green to this red, this is minus pi over 2, if you want to think of it like that. And then we want this bit to be less than or equal to pi over 4. Pi over 4 is 45 degrees. So we show that using a solid line. That would be something like that, okay? And this point has coordinates minus 3, 4. The center of the circle has coordinates, if I show this in black, this has coordinates 0, 4. And we want the region essentially everywhere here, if that makes sense. Okay, so that's the region we want, and therefore to satisfy both these conditions, the region we want in total would be this region in yellow. Okay, so this region shown highlighted over here is the region we want. Okay, so this satisfies the set of points for this bit over here. Okay, so hopefully that makes sense. And now for part B, we have to find the maximum value of the argument of w in the interval minus pi to pi, give your answer in radians correct to 2 decimal places. Now, the first thing, we want to rewrite this in the form w minus w1, okay? And we know that this is equal to 3. So with that being said, if we consider w minus 4i, that would be the same as, if I just write it here, w minus 0 plus 4i. So essentially, what we have over here then, as we did before, we have a circle with center 0, 4 and radius 3. Essentially the same circle we had over here. And I've drawn that over here. And when we talk about the maximum argument of z, that will be essentially, if we think about our origin, our maximum argument would be this over here, okay? Our maximum argument would be this entire angle over here. And we'll call this angle theta. Now, in terms of what we can find out, if I get a different colour, we have over here this angle over here, which is pi over 2. And you will also notice, if I go back to the black pen, we have a radius of length 3. This length over here is 4. And therefore, we want to find out in this question, if I grab a different colour, we want to find out this angle, and we can find that using trigonometry. So first of all, if we find that angle, that would be the inverse tangent of 3 over 4. Okay. And then we also have this pi over 2 over here. So we add on pi over 2. And therefore, we can conclude over here that theta is equal to the inverse tangent of 3 over 4 plus pi over 2, which is 2.21. Okay, so we have 2.21 radians. Okay. Question 9. An octopus is able to catch any fish that swim within a distance of 2 meters from the octopus's position. A fish F swims from a point A to a point B. The octopus is modelled as a fixed particle at the origin. Fish F is modelled as a particle moving in a straight line from A to B. Relative to O, the coordinates of A are -3, 1, -7, and the coordinates of B are 9, 4, 11, where the unit of distance is meters. For part A, we have to use the model to determine whether or not the octopus is able to catch the fish. Well, the worst case scenario for the fish is when the octopus is directly below F. Okay, so if you've got your fish and then if the octopus is directly below it, that will be the shortest distance between the octopus and the fish. And essentially, we need to find out if the distance between the octopus and the fish is less than 2 meters. It's quite complicated to think about this question. If over here you've got your points A and B, let's just draw a line. You've got your point A and B, which have coordinates -3, 1, minus 7, and 9, 4, 11. Now, it doesn't matter where f is. F could be anywhere on this line, for example here. And the worst case scenario is when f is directly below, when f is directly above O. Okay, so let's just draw this on. And the reason for that is, if you think about it, if the fish is directly above the octopus, this line over here is the shortest distance, and this is the shortest distance, and if the minimum distance of OF is less than 2, then the octopus can catch the fish. Okay? Now, it doesn't matter where F is. If, for example, I'll do this in a different colour to demonstrate. If suppose F is over here instead, then F being here is better for the fish because it's further away from O. But we're looking at the worst case scenario, and that's when the octopus is directly below the fish. Okay? So with that being said, you will notice over here we have a right angle, and we know F lies on AB. So what we can do is we can find an equation for F, rather find the coordinates of F, and then if the distance OF is less than 2, the octopus can catch the fish. Okay? So we need to find the equation of OF, and then find the distance OF, and if that distance is less than 2, then the octopus can catch the fish. Remember, the worst case scenario is when the octopus is directly below the fish. And because of that, when the octopus is directly below F, OF and AB intersect at 90 degrees. Now, let's begin by finding OF. But before that, we need to find AB. The vector AB, that will equal the vector OB minus the vector OA. So we have 9, 4, 11 minus 3, 1, minus 7. We end up with 12, 3, 18. So therefore, OF will equal minus 3, 1, minus 7 plus some value, lots of 12, 3, 18. Okay, and of course lambda changes as you move across AB. And since AB and AF are perpendicular, so since the vector AB and the vector OF are perpendicular, we can then say that the vector AB dot product with the vector OF equals 0. So with that being said, we have the vector AB 12, 3, 18 dot product with the vector OF, that would be minus 3 plus 12 lambda, 1 plus 3 lambda, minus 7 plus 18 lambda. This is equal to 0. So with that being said, we have 12 lots of minus 3 plus 12 lambda. We have 3 lots of 1 plus 3 lambda. And then we have 18 lots of minus 7 plus 18 lambda. All of this is equal to 0. 12 times by 3 minus 3, that's minus 36. 12 times by 12, that's 144. 3 times by 1, that's 3. 3 times by 3, that's 9. 18 times by minus 17, that's minus 126. 18 times by 18, that's 324. So if we simplify all this, we have 477 lambda minus 159 equals 0. Lambda is equal to 1/3. So knowing that lambda is equal to 1/3, we can find out what the coordinates of f are by substituting 1/3 into here. So therefore, OF is equal to minus 3, 1, 7 plus 1/3 lots of 12, 3, 18. So we have minus 3, 1, 7 plus 4, 1, 6. So we have minus 3 plus 4, which is 1, 1 plus 1, which is 2, 6 plus, this should be minus 7 plus 6, that would be minus 1. So therefore, F has coordinates, if I add it here, 1, 2, minus 1. So with that being said, we can find out the distance OF. Distance of OF will equal 1 squared plus 2 squared plus minus 1 squared square rooted, the result of which is root 6. Now root 6 is equal to, if I work this out on the calculator, root 6 is equal to 2.44, etc. And obviously this is greater than the 2. And because of that, we can therefore conclude that the octopus cannot catch the fish. Okay? Now, for part B, we have to criticize the model in relation to the fish, and then criticize for part C the model in relation to the octopus. We have the following reasons. So the fish may not swim in an exact straight line from A to B, hopefully that makes sense, and for part C, the octopus may move from its fixed location on. Now that concludes the end of the paper. Don't forget to like, share and subscribe. Any questions, please feel free to comment them in the comment section below, and hopefully I'll see you guys in the next video.